standard. Okay, right, this standard is one of the basic standards that you need to know. It covers things, as you can see from the title, your bonding structure, properties, and energy changes. So what is it all about? Bonding and structure. You've got to know ionic, covalent, and metallic bonding, and we'll do that in more detail in the next lesson. And intermolecular forces. Again, we'll do that in the next lesson. Then this is what we're going to focus on: Lewis structures, shape, and polarity. And then you do the application. So basically, why does copper conduct electricity? Why can you mold gold to form rings? Why? But you can't do the same to salt. That's the focus of the standard, to try and explain the properties of the substances. So the other part is energy changes. So this is where your calculations come in. You know, that's why you're doing the 2011 and 2012 before this standard, because there are some calculations, so you have to know about the mole for that. And that's exothermic and endothermic reactions. You know, we will discuss this later, so don't worry about that. But you can see the calculations. And then finally, the properties. And that's what I said, that's the whole point of the standard, is to be able to explain the properties. So that's why you need the bonding and the Lewis structures and the everything else. So why is it ductile, which means it can be drawn into wires? Why can you shape it malleable? Why has it got a high boiling point? So what we're going to focus on this lesson is Lewis structures, shapes of molecules, and the polarity of molecules. And in the next lesson, we're going to use that information to discuss intermolecular forces and therefore the properties. Any questions before we go on? Because that's a very quick overview of the standard, or what you need to know. The booklets sometimes go a little bit more detail here and there for background, but this, for the exam, this is what you need to know. Okay, right. Isabella, that is going to come up in this lesson, so that will come up. Okay, right, and we'll do it as we go through the lesson, so if you can just hold on that idea. Okay, first of all, you will be given a periodic table in the exams and in tests and so on. You're always given one. Use it. Okay, you've got one, great. I mean, of course, in the exam you can't take your own one, but you will be given one. So because you know a lot of things from the periodic table, you know where all the metals are. So they're on the left. Hi, Jerome. So they're all on the left, and then of course you should know that the non-metals are all on the right, top right. And then those green ones in the middle are the metalloids. Those are the ones that look like metal, so they're shiny or something like that, but they don't have all the properties of metals. And we'll explain properties later on. Okay, and then of course the noble gases, which is group 18, are the ones that don't bond. Next year you'll find out that if you push xenon and so on with enough pressure, it will bond with oxygen and fluorine, but basically, as far as you're concerned, the noble gases do not bond. Okay, so use the periodic table to work out valence electrons. Now, when I say valence electrons, do you know what I mean? So a few yeses or a few no's, you do, okay. You used to know, right. Valence electrons are, of course, orbiting around the nucleus. So what they do, they're just not random, they're in fixed energy levels. So the outermost energy level is the most important, because when these atoms collide, it's the outermost part that's going to, you know, be in contact with another atom. So we aren't concerned about the inner ones. They have an effect, but they're not key to the bonding. So you have to count how many electrons are on the outermost energy level. And that's the valence energy level, and therefore the valence electrons. So you've got in group 1 down here, there's 1 electron in the valence energy level. Group 2 has got 2. We're going to skip all these transition metals. Next year you do that in more detail. Group 13 has got 3 valence electrons. Group 14 has got 4, 5, 6, 7, and then group 18 has got 8 valence electrons. That's a full energy level for group 18. All the others are not full. So that's sort of a quick explanation. So, you know, I've talked about the full energy level. So this is where we come up with this octet rule. Atoms are more stable, so they have less energy and therefore are less likely to react when the energy level is full, the outermost one. So that's why the noble gases don't react, because they've got a full energy level. So they're stable, they don't have much energy, and they don't, or the electrons don't have as much energy, and so they just, you know, don't bother reacting. The octet rule is, yes, Sufyan, I hope I got your name right. They will try to be like noble gases, so they're going to try and get electrons or lose electrons or share electrons or do something to the electrons to get a full energy level. And this is where this octet rule goes. So what I'm trying to show here is water. So hydrogen has only got 1 electron, that's this green one, in its energy level. Here's another hydrogen with a its electron. I've just made it green just to differentiate it. And then we've got oxygen here. Now oxygen has got 2 energy levels, that's the inner one, and then the outermost one. And in the outermost one, if you count the red electrons, there are only 6. So it's not 8, and it wants to get 8. So the way water works is that it shares electrons. So oxygen will share one of its electrons with one of the hydrogens, and the hydrogen will share back, and same for the other hydrogen. And that sharing is a covalent bond, correct. So this is how we get an octet. Now notice hydrogen does not have an octet. There are 3 elements that won't have octets because they don't really have a second energy level. And that is hydrogen, helium obviously, and beryllium. That is in the next energy level, but it can, and even boron can sort of do without that. It doesn't need an octet. Now again, you don't really have to know it, or you're not expected to know it. You may be given it in an exam with a Lewis structure and just presented, so you have to accept it. This is how it is, but you won't have to explain it. At level 3 you would have to explain why. Right, so let's carry on. So this is the periodic table of the first 20 elements, but what I'm trying to highlight here are the electrons. So remember I said in group 1 there's 1 valence electron. So we can draw structures, and it was a chap called Lewis in the 1800s who worked this out. And he represented the way elements bond by using dots for the valence electrons. So if you have a look, hydrogen, lithium, sodium, potassium, they all have 1 dot. Okay. Group 2, beryllium, magnesium, calcium, all have 2 dots. And you can see group 13, because we've skipped out all the transition metals, group 13, 3 dots, group 14, 4 dots, 5 dots, 6 dots, 7 dots, and group 18 has got 8 dots. Okay, and so basically you have to, when you draw these structures and they bond, okay, bye. So when they bond, you want to land up with 8 dots, because that's like the octet rule. So let's get going. How do we draw Lewis structures? If you follow these rules, it's very easy. Just be methodical. So you draw it for molecules. You can draw it for ions, but at level 2 we don't. We just draw it for molecules. And by molecules I mean non-metals covalently bonded to each other to form discrete units. Sorry, because there are exceptions. So you show all the valence electrons as dots. Okay, you show a bond by pairing dots, and you have a pair of dots between two elements to show the bond. And you can represent it as a line. That's called a modified structure. So here's an example of a Lewis structure with nitrogen. It's bonded to hydrogen through this pair of dots, or you could show it as a line in line H. So both are acceptable. Okay, it's not that one's wrong and one's right. Okay, and why do we use this? You're going to find you're going to have to draw Lewis structures all the time to work out the shape and the polarity of the molecule, because the shape is determined by the number of regions of negative charge around the central atom. And that's why if you've drawn the Lewis structure, you can quickly see I've got 4 regions around the central nitrogen atom. So you can then carry on from there what the shape would be. Okay, so let's look through the rules. You first say I'm doing PF3. You count the total number of valence electrons. So phosphorus, do you have a periodic table handy sort of close by? Then you can answer this question, because if you think of phosphorus, how many valence electrons does phosphorus have? Or if I say phosphorus is in group 15, would you be able to tell me how many valence electrons it has? 5. Correct, Caitlin. Right. Fluorine is in group 17. How many valence electrons does fluorine have? Okay, there's a race on. Great. Good. Both of you correct. Yes, 7. So I've got 1 phosphorus, so it's 5 from the phosphorus, and I've got 3 fluorines, so it's 3 times 7, 21. So overall, I'm going to have 26 electrons. So 21 from the fluorine and 5 from the phosphorus gives me 26 electrons. So my final Lewis structure must show 26 dots. So when you've finished your Lewis structure, count and check, because it's so common to forget the ones around the fluorine. You know, people just concentrate on the bonds and forget about the rest. Now, step 2 is the hardest bit in a Lewis structure, because you have to work out what is the central atom. Now, there are a number of ways you can work out what you would expect it to be. The first thing you need to think of, which one has the highest valency? Now, valency is not the same as valence electrons. Valency is the combining power. So, for instance, phosphorus is in group 15. It has 5 valence electrons, but it will bond to 3 other, you know, it can combine, say, to 3 hydrogens. So it has a valency of 3. Fluorine is in group 17, so it has 7 valence electrons, but it has only a combining power or valency of 1. So if you were going back to the periodic table, let me actually just click on this. Okay, I don't know if that's very clear. This would have a valency of 1. Can you see what I've got here? I've shown the periodic table. I just want to check that we are looking at the same thing. Yep, okay. So this is a valency of 1. Valence, sorry, you can't see my cursor. Group 1 has a valency of 1, group 2 has a valency of 2, group 13 has a valency of 3, group 14 has a valency of 4, and then when we get to group 15 it starts going down again. It's now 18, subtract the group number for valency. So group 15, it has 5 valence electrons, but 18 subtract 15 is 3. It's got only 3 I'm trying to work out why. Okay, I'll just move this over. It's only got 3, a valency of 3. Group 16 has got 6 valence electrons, but 18 subtract 16 is 2. So it is a valency of 2. So combining power of 2. Now, electronegativity is not the same as valency. Valency is the combining power. How many other atoms can it combine with? you know, if it's, so like hydrogen has got a combining power of 1, so it can only combine with one other thing that has a combining power of 1. Or if it combines with oxygen, oxygen needs to combine with 2. So that's a sort of very brief summary of what valency is. So I'm just going to take this down again. And move it out. Okay. Electronegativity is how strongly that atom attracts the bonding electrons. So it's not with how many, it's with how strongly it attracts the bonding electrons. So phosphorus has got a valency of 3, fluorine valency of 1. So phosphorus is going to be the central atom. The other way you can work out what's the central atom is the one that's normally there in the least number. So phosphorus is only 1, fluorine is 3 of them. So it's unlikely that there's going to be a fluorine in the middle surrounded by other fluorines and phosphorus. It's going to be phosphorus in the middle surrounded by fluorines. Those are the two main ways, and as we work through, you'll sort of come, you'll start getting a gut feel. But it's generally always the valency, and if you're not sure about the valency, look for the one that's the least there. So like it'll be phosphorus. So here we've got phosphorus, and fluorine can only form one bond, so it can never be in the middle, because it can't be in the middle and bond to 2 other fluorines and phosphorus, because it's only got a valency of 1. Okay, so if I wanted to draw the Lewis structure, I now take from my 26 dots, I arrange a pair between every atom. So I put my phosphorus in, and I've arranged the fluorines around it. Doesn't matter how you arrange it around it, what angles, just put the fluorines around it. And then put a pair of electrons between each P and F. So I've used up now how many electrons of my 26? 6. Right. So I've used up 6 electrons. It means I've got 20 still to arrange. So step 4 is put the remaining electrons in pairs around the outer atoms, so that each outer atom has an octet. So if we go for it, so there's 2, so we're down to 18 now, down to 16, down to 14. That fluorine now has an octet. It's got 8 dots around it. So I go to the next fluorine. So now we're 14, 12, 10. Okay. That's got an octet now around it, 8 dots. So I go to the next one. I've forgotten, I've lost count. Well, anyway, we'll count them up now. So I've given an octet around every fluorine. And if you count there, I should have used up 24 electrons. Great, Caitlin. That's correct. So you can't stop there. I've still got 2 electrons I haven't assigned. So if I've still got anything left over, I place it on the central atom. Okay. So when I've done that and I've used up all my electrons, now I check for octets, because you'll find that sometimes you won't have octets. And then you've got to do other things. So there's my Lewis structure that I've just drawn. Look around each atom. Do they all have 8 electrons around them? Yes. And if you've done that, you are pretty sure that your Lewis structure is perfect. Okay. So that is the Lewis structure for phosphorus trifluoride. If I now go to the next one, so this is methane, CH4, we do exactly the same thing. You first count the number of valence electrons. So you go to your periodic table, you look for carbon. Carbon is in group 14, 4 valence electrons. Fantastic. You look for hydrogen, it's in group 1, so it's 1 valence electron, right. So what you've got 4 hydrogens, so I've got 4 from carbon, 4 from the hydrogens, so I've got 8 in total. Okay, so I've got 8 dots to distribute. What do you think will be the central atom? So we're now on step 2, identify the central atom. Carbon, correct. and it's because it's got the highest valency. It's got a valency of 4 compared to hydrogen, or the other way you could look at it, it's the one there that's in the least amount. I've got 1 carbon and 4 hydrogens. So we've got that bit. Now we do the same thing. We draw the carbon in the middle and the hydrogens all around it. And now we do the step 3 of putting those electrons in each bond. So I've got 2 for that bond, 2 for that bond, 2 for that bond, and 2 for the last bond. And do I have any electrons left over now? You sure, Caitlin? I've got 8 electrons that I must distribute, and so I've got 2, 4, 6, 8. Yep. Okay, so this is, you do a lot of counting in chemistry. Whether you're balancing equations or anything, it's you counting. So I've used up all my 8 electrons, so I can't do step 4 and I can't do step 5 because I don't have any electrons remaining. So we go straight to step 6 and we go hydrogen. Now I did say check for an octet, but remember that hydrogen only has 2 electrons. Okay, so each hydrogen is happy, and look at the carbon. The carbon has got 8 electrons. So do you think that Lewis structure is correct? Yes. Okay, so I've got things, you know, all sorted. So let's do this one, H2CO. And this is where you want to know the valency rule for the central atom, because you can see I've got 2 hydrogens, 1 carbon, 1 oxygen. So you go, which one of carbon and oxygen is the central atom? So think about which one's the valency, because I'll ask that, highest valency, because I'll ask that just now. But let's first do the number of, okay, there's a race going. Okay, just think of the highest valency, not highest electronegativity. So in other words, the combining power. Oxygen is in group 16. It has 6 valence electrons, but its combining power is 18 subtract 16, which is 2. So correct there, Ines and Caitlin. Okay, so I think Emma and Cooper, you were confused between valence electrons and valency. So I agree oxygen has the highest number of valence electrons, but it doesn't have the highest valency. Okay, because it's 18 subtract 16. So now we count the number of valence electrons. You were also most probably thinking of step 1 where we're looking at valence electrons. Hydrogen group 1, 1 valence electron. Carbon group 14, 4 valence electrons. Oxygen group 16, 6 valence electrons. So it's 2 from hydrogen, 4 from carbon, 6 from oxygen, gives me 12 dots I need to distribute. So the central atom, as we've done just now, carbon has the highest valency, so carbon will be in the middle. Okay, so I put carbon in the middle, so I'm now on step 3. Now I take my dots and I arrange it in pairs as a bond between each carbon and hydrogen and carbon and oxygen. So 2 there, 2 there, and 2 there. Now I go, I've used up 6, so I've got 6 electrons still to remain, remaining, so I've got to go into step 4. So now can you see I've started putting it around oxygen? Why didn't I start around hydrogen? You know, it says there, place the remaining electrons in pairs around the outer atoms. Why didn't I start around hydrogen? Okay, because hydrogen already has enough. Correct. Brilliant, both of you. Okay, so it's only oxygen that can have more and that can have an octet. So we go 2, 4, 6, and plus the bonding pair between carbon and oxygen, it's now got an octet. Do we have any electrons left that we need to still put somewhere? Or have we used up all 12? Correct. We don't have any left. We've used up all 12. So we've done step 4, we've done step 5, now we're on step 6. So with step 6 we go, well, hydrogen's happy, okay, oxygen is happy, but what about carbon? Is carbon happy? Does it have an octet? No. So when we've got this, we can't just put another 2 electrons in to make carbon happy, okay? Because we can't materialize electrons out of nowhere. We have to make oxygen share more of its electrons. Hydrogen can't share anymore because it's already sharing its electron. So the only source is from the oxygen. So we have to move electrons from oxygen to be shared between carbon and oxygen. In other words, it has to go from a lone pair or a non-bonding pair on the outside. It's got to go between carbon and oxygen as a bonding pair. So if I draw it again, basically, doesn't matter which pair you use. We're not worried about how you arrange things in Lewis structures. It's just as long as they've got the octet and you've got the central atom and so on. So you could have taken the top pair, you could have taken the bottom pair, it doesn't matter. So I've taken one pair across, and now you check again for your octet. Carbon now has 8 electrons, because it's all the ones that's being shared, those 4 plus the 4 being shared with hydrogen. So is that a correct structure? Yes. Okay. Right. So into, this is the last one we're going to do in full like this. I've only got 2 atoms. Okay. Nitrogen is in group 15, so how many valence electrons? 5. Because I've got 2 of them, how many have I got in total? 10. Correct. Dead easy. What's the central atom? Nitrogen. Okay. In fact, there's no real central atom because, or you can pick which nitrogen and say the other one's around it. I don't know. Okay. So we're on step 3 now. You draw your 2 ends. You put in your bonding pair of electrons. Now we've got 8 left, so we put our things around the nitrogen. That nitrogen is now happy, it's got its octet, but we've only used 8 electrons, so we've got 2 left, so you put it around the next nitrogen. So I don't have any more nitrogens left, so I have to skip step 5, because I'm at my maximum now. So we're at step 6 now. You check for the octet. So that nitrogen is happy, but that one isn't. So what can I do to give the nitrogen with a red circle an octet? To move electrons. So move the electrons from the nitrogen on the left, the non-bonding ones, and put them between the nitrogen. So I can move that one. I'll flip it around just now. But you can see the one on the right still doesn't have an octet. I've only got 6 electrons for the right-hand nitrogen. So I have to move another one. And then I'm just going to flip that one around. Now, can you see, normally it's written with a lone pair of nitrogen on the right-hand side, so it looks all linear, but that's still totally acceptable. So that's an example of a triple bond, where we have 3 bonding pairs of electrons between the 2 atoms. Okay, now, I know people write those middle dots differently. You know, here I've stacked them up vertically and horizontally I've also seen. The conventional way is stacking them up vertically like I've done there. If you wrote them horizontally like nitrogen, double dot, double dot, double dot, nitrogen, it won't be marked wrong. But conventionally we tend to stack them up vertically like that. Yep. Okay. So we've got the right number of electrons, correct octets, so that's the correct Lewis structure. Okay, now I was going to, but I'm just seeing the time. We might come back to this, okay, for practice, because I want to actually spend more time on the polarity, because we've got to do Lewis structures again with the polarity. Are you happy to move on? Yep, okay. So we'll just flick on to, come on, there. Okay. Once we have the Lewis structure, you can work out the shape. Now normally in the exam you get asked to draw some Lewis structures, and then in another part of the question you get given Lewis structures and you have to discuss shape. that's just so in case you can't draw Lewis structures, you can still discuss shape. But sometimes I've noticed they tell you to draw the Lewis structure and then to discuss shape. So of course, if your Lewis structure is wrong in the first place, your shape is going to be wrong. So make sure you know how to do the Lewis structures, and then you can do the next step. So tips for this one is learn the shapes off by heart. This is the donkey work. You've got to just know the shapes. And I'll show them just now, but it's things like linear, tetrahedral, trigonal, planar, so on. You'll see them just now. Then, when you've done your Lewis structure, you count the number of regions of negative charge around the central atom. And that'll give you your electron geometry. So, and I'll explain that just now. I think it's easiest if I just quickly go through this and we'll repeat it when we do it. When I say about the number of regions of negative charge, a single bonding pair of electrons is one region of negative charge. A lone pair of electrons, a non-bonding ones, like the ones that were around the fluorine, are each pair of non-bonding electrons is a region of negative charge. Double and triple bonds, like the one we had between the C and the O and the nitrogen, that's group of 6 electrons, or that group of 4 electrons that are being shared between the two atoms, is considered one region of negative charge. Okay, just so that you know that. And then when you know the electron geometry, then you can work out the molecular shape. And I think I'll do this first before I go on to FET. So here are the shapes that you need to know. If I have 3 atoms or 2 atoms like nitrogen in a row, it's a linear molecule. Around my central atom, I only have 2 areas of negative charge. This and this on the right-hand side. I don't have any non-bonding pairs of electrons. I only have a region over here and a region over there. So it's linear. If you've got a molecule with only 2 atoms, like nitrogen, N2, any molecule with 2 atoms will be linear. It's like if I say I can draw a straight line between Wellington and London. I mean, obviously you can, because I've only got 2 points. But can I draw a straight line necessarily between Wellington, Paris and London? The moment you get a 3rd point, you may not be able to draw a straight line. Does that make sense? Yeah. Okay, so if you've only got 2 points, you can always draw a straight line between them. Okay. Trigonal planar is the name of the shape that has got, so here's my central atom. I've got 1, 2, 3 regions of negative charge. In this case, I don't have any non-bonding electrons. They're all bonding. So I've got 3, it's trigonal planar. A way to perhaps remember it is tri means 3. I know some teachers use triangular planar. That is not correct. It hasn't been marked wrong, but it's not really the right word. The right word is trigonal planar. But if you know it as triangular planar, it is accepted. Planar, it's because this molecule is actually flat, and we'll see that just now. Then if I've got 4 regions of negative charge, then I get the tetrahedral shape. So here I've got 4. So why do I get these different shapes? Electrons are negative. So what do you know about negatives and negatives? What do they do to each other? They repel. So you have to say that when you explain it, you have to say, for instance, linear, I've got 2 areas of negative charge, and the electrons repel each other as much as possible, so the molecule is arranged in a linear shape with a maximum bond angle of 180 degrees. Because they can't, if they try and get away, further down here, it's getting closer on this side. And the same thing over here. I've got 3 areas of negative charge. So they're going to, the electrons will repel each other as much as possible, so the furthest they can get from each other is 120 degrees. So it's trigonal planar, and so on. Okay, and remember, of course, it's in 3D, so this is where the tetrahedral comes up. It's not 90 degrees, it's 109 degrees, because it's not flat, it comes out. Let's look at the when we have non-bonding electrons as well. So if I have no non-bonding electrons, only bonding ones, then it's what we saw before, linear, okay, trigonal planar. So this is the number of regions of negative charge. But I can, for trigonal planar, I can make, say, remove this atom and have a lone pair of electrons here. And so there it is. So I still have a bond angle of 120, but my molecule is now bent. It's like I've taken the molecule and I've bent it. So it's not trigonal planar anymore. So you have to know that if I have got 3 areas of negative charge, of which 2 are bonding and 1 is a non-bonding pair of electrons, then it's a bent molecule. So here's just some basic learning work you have to do. And tetrahedral we've seen, but if I replace one of these with a non-bonding pair, then I get the trigonal pyramidal shape, and if I remove 2 of them, I get the bent shape. So this is like water, and we'll look at examples now. So what I quickly want to do, I'm going to just escape from there, and I'm just going to look at some molecular shapes very quickly. So here's an example of linear. This is FET. If you Google FET, I'll spell it over here. So if you go right, FET molecular shapes, if you Google that, you're going to get this. Okay? And this is quite good because it shows that bonds aren't fixed or rigid. You can actually, they will move around, but they will eventually, if I try and bring it closer to that one, they'll eventually always try and repel each other. Okay, so here's, as I say, my linear molecule. If I add a bond, it becomes a trigonal planar. If I add another one, it becomes a tetrahedral. And you can see it is in 3 dimensions. Every bond angle is 109 degrees. Next year you learn about more of them. Okay, but for level 2 you only have to know those 3 basic shapes: linear, trigonal planar, and tetrahedral. But we can also now, of course, have lone pairs. So if I did that, and now I added a lone pair of electrons, can you see that lone pair has repelled these? So they're now closer. And what is this bond angle now? So think of how many regions of negative charge have I got? Okay, it's a bent molecule. And what do you think the bond angle would be? So if this is 360 degrees around the whole central atom, what would be the angle between this bond and that bond? Okay, you're being very specific, Michael. 120 degrees would have been fine for me. I do explain in the booklet that it's slightly less than that, but if you just said 120 in the exam, that would be fine. Okay, so yep. So because I've got 3 areas of negative charge, so a common question would be like, SO2 has got a bond angle of 120 degrees, but water has only got a bond angle of 109. Please explain. Then you would have to draw the Lewis structure and say, well, SO2, which this molecule can represent, has got 3 areas of negative charge, of which 1 is a non-bonding pair. So because I've got 3 areas of negative charge, the electron geometry is trigonal planar, and so my bond angle will be 120 degrees. But water has got 4 areas of negative charge, 1, 2, and the lone pair and another lone pair. So it's going to have, the electrons will repel each other, but they can't escape from each other as much, so that they're going to be closer together now. So this will be now a bond angle of 109. So does that make sense in working out how to do the shapes? Okay, right, let's go back to this, and right, so sorry, I'm just going to go flick through this again. Okay, so now learn the electron geometry and the molecular shape to discuss the bond angle. So remember I said for that water, there are 4 areas of negative charge around the central oxygen atom. So it's going to have an electron geometry of tetrahedral, but the molecular shape is going to be bent because it's got 2 non-bonding pairs of electrons. So can you see the level of detail you need to have in your answer? Don't just say it's bent because it's got 2 lone pairs. That's not enough information. Start always that it's got 4 areas of negative charge, tetrahedral shape. They repel each other as much as possible. So the bond angle would be 109 degrees, and then you can drill down to the tetrahedral, to the non-bonding and bonding electron pairs. Okay, any questions before we move on? No. Okay. Right. So here's some examples. Let's see how much, I don't expect you to remember these off by heart after listening to them so much, but let's have a go. This first one over here is carbon dioxide. What is its shape? Linear, correct. This one here is like BF3 or, yeah, so the electron geometry is linear and the CO2 is linear. This one, what is its shape? So the orange and yellow one like B3, trigonal planar, correct. Now Caitlin, don't just say trigonal, okay? Because you can get trigonal planar and you can get trigonal pyramidal. So if you just said trigonal, okay, yeah, that's right, fine. But I have seen students do that. They just say trigonal and they won't get anything. Okay, so if you have to explain this, you have to say there are 3 regions of negative charge or electron density. It doesn't matter which one you use. Please do not say there are 3 regions of electronegativity. I've seen that quite often. Electronegativity is the attraction to a bonding electron. It's not a thing. I don't know if that makes sense, but what you want is electron density or negative charge. It's not an attraction. This is a region, a something, not an attraction. Does that make sense? So you won't use the word electronegativity. Okay, so here the electron geometry is trigonal planar and the shape is trigonal planar. Now, oh, sorry, I clicked too soon. Okay, here the shape is bent, but it's got 3 regions of negative charge, so it's a trigonal planar electron geometry and a bent molecular shape. So let's go back to water. What is water? The shape. Bent. Okay. Now notice I have 2 bent shapes, but they don't have the same bond angle. Remember the SO2 has got a bond angle of 109 and water has got a bond angle of, let me say that again. SO2 has a bond angle of 120 and water has a bond angle of 109. So remember there are 2 bent shapes. Okay, just like, linear, you can have linear for a number of molecules if there's just 2 atoms in it. Right. How about this one? This one is ammonia, NH3. What is its shape? Okay, the electron geometry is tetrahedral, Caitlin, because it has got 4 areas of negative charge. So the bond angles will be 109. But because the nitrogen has got 1 lone pair, the shape name changes from tetrahedral to, correct Michael, to trigonal pyramidal. So think of this as a pyramid, the nitrogen being a bit higher than the hydrogen. So the nitrogen with the 3 hydrogens pointing down. Okay, so it's a tetrahedral electron geometry that gives you the bond angle, and then the shape is trigonal pyramidal. And then the last one is methane, and what is its shape? Tetrahedral. Okay, great. So what we've done so far is Lewis structures and then shapes. You need to know the Lewis structure before you can get onto the shape, because you need to know how many lone pairs are around the central atom, or if there are any. Okay, yep, so here because there's no lone pairs, the electron geometry and the molecular shape is the same thing. Right, and we're not going to practice again. I'm hoping there will be a bit of time for polarity at the end. Okay. Now, somebody asked about polarity in the beginning. So, what is it? A molecule is polar if there is a difference in the distribution of charge around the central atom. In other words, if one side is a bit more negative and the other side is a bit more positive. So the word polar comes from like a bar magnet. You know, you've got a north pole and you've got a south pole. Okay, so you've got basically a positive pole. This is represented as blue. It doesn't look blue, obviously, but we represent it as blue. So a positive pole where there's not much electron density, and fluorine, which has got a high electron density. Now, what causes this unevenness of distribution? Just checking to see what your ideas are. Okay, some of you are typing. Electronegativity. Right. At level 3, you learn why there's this difference of electronegativity. Here at level 2, basically you have to know that each atom has got, or each element has got a different electronegativity to another one. So if I just go, okay, I'm just going to escape from here and do this one. Okay, so I'm going to show, okay, it doesn't show the electronegativity here. Basically, the more you go to the right of the periodic table, the more electronegative it is. And bottom left, the least electronegative it is. So let's take atom A over here, and can you see this word, or is it too tiny? It says electronegativity. Okay, you can see it, right. So I don't have a very high electronegativity for A, and B has got a higher electronegativity. And if I make it higher, can you see what happens to that arrow? It gets longer to show it's a bigger difference. So that arrow represents what we call a bond dipole, if you look over here. Now, what is a dipole? All a dipole is a separation of charge. So you can't have a negative dipole or a positive dipole, because a dipole being a separation of charge means that one end must be negative and the other end must be positive. So you've always got a negative and a positive in a dipole. One end will be negative and the other one will be positive. And by convention, we always show the arrow going from positive to negative. Okay. Has anybody ever done vectors in physics? I'm not quite sure if it's a level 2 topic for physics or a level 3 topic. You haven't done physics? Yep. No, just for those people that know. Okay. If you've done vectors, you're doing physics and you're doing vectors, a dipole is a vector. Okay, you add it like vectors and you subtract them like vectors and so on. For those of you not doing physics, don't worry about it. Okay. So if I make the electronegativity less, then can you see the separation of charge gets smaller? I've got less and less difference between the negative and positive end of the molecule until eventually there's no difference because they've got the same electronegativity. So if I try and show the, let me do it like this in terms of colors. So here it's showing as white because there's an even distribution of electron density around there. If I increase the electronegativity of B, it becomes more and more negative because it's attracting these bonding electrons between A and B, and it's sucking them more and more to the B, so B is getting more and more negative, and A is getting less and less negative, more and more positive, because the shared electrons are being pulled away. Okay, so electronegativity is just a measure of how strongly an atom attracts these bonding electrons. Okay, so that's how I can make this pretty negative and that one's pretty positive. Okay, this would be considered an ionic bond by now because B has just about taken those electrons so much A doesn't get a look in. Okay, so 3 atoms, I can do the same thing. I can show my, here it doesn't actually show, but if I change the electronegativity, I've made that one higher, then you can see I'm getting more and more of a dipole. And if I make this one more electronegative, you can see how it moves, how the yellow here shows the overall dipole, molecular dipole. I can make the black ones there. A is not very electronegative, so B grabs those electrons, okay? But C is more electronegative, so it's grabbing those electrons, so there's a sort of overall negative area over here and a positive area around A. So we can see this in the real molecules. If I show the electrostatic potential and I'm showing the bond dipoles, it comes out as gray, but you can see I've got so here I'm just showing the electronegativity. It's a Pauling scale if you're interested. Hydrogen is 2.1. Eventually you'll know these off by heart. Fluorine is 4, so it's a lot more electronegative. It's nearly double as electronegative as hydrogen. So my molecular dipole is showing from this positive area going to the negative area. If I change it to something like water, I don't know if you can see this area is positive because I've got a bond dipole going between the hydrogen and oxygen because this is a polar bond. It's an uneven sharing. Don't worry, Caitlin, I'm condensing, you know, a whole booklet that will take you sort of 2 weeks and 1 hour. So, you know, that's why we record the lesson, that you can also go over it when you're doing your booklet as well. I've got a bond dipole going from this between this hydrogen and this oxygen, a separation of charge, because I have got hydrogen with a lower electronegativity and oxygen with a higher electronegativity. So my yellow over here is my, if you want to see the colors more clearly, I can, oops. So there's my one bond dipole, there's my other bond dipole, and my molecular dipole is around the oxygen. It's up here. Okay, this will be the positive area. If I go and do a few more, you are welcome to do this yourself. Let's do ammonia. So when you go and play around, just Google that FET and then you can see it. So there's your ammonia. It's got your hydrogens, and the nitrogen is more electronegative. So hydrogen is 2.1, nitrogen is 3. So that's why the dipole goes, the molecular dipole goes towards the nitrogen. Okay, now, when I talk about polarity, you can see this molecule is polar, can't you? Because I've got obviously a negative end and I've got a positive end. So how do I work out if something is polar or not? We look at, first of all, the Lewis structure and the shape, and then we work out if the molecule is symmetrical. And I might go to something like water. Okay. Now if you look at water, is that molecule symmetrical? And it's a bit of a trick question in some ways. So does anybody want to be brave enough and have a yes and no? Okay. Overall, it is not symmetrical. Molecules can have a number of different planes of symmetry, and for a molecule to be totally symmetrical, every single plane of symmetry must be symmetrical. So what do I mean by plane of symmetry? Basically, if you take a knife or something and you cut through the central atom along a bond or exactly between a bond, the mathematical term is bisect. Do you know what I mean when I say bisect? Yep. Okay, so let's take oxygen, because oxygen is one. So here, if I cut it through this oxygen down the middle, because it's a central atom, right exactly halfway between this bond and that OH bond, so right down the middle, do you all agree that this half looks exactly the same as the right-hand side? Yep. So it's got a plane of symmetry. So yes, it looks symmetrical. But I can do exactly the same thing, because you've got to do the plane of symmetry across every bond and every bisection. So I can take this bond hydrogen-oxygen. So if I draw a line between this hydrogen and oxygen, so it's going along over here, is this side equal to that side?